So one example of how you can use this to study phenomena that is of interest in solid-state physics, for instance, but also more generally, is disorder, right, and localization. So there have been many strategies to localize light, okay, using this kind of equations, okay, this kind of framework. And here I'm giving you a few examples. So, for instance, you can localize light in a defect in a photonic crystal. You can use flat bands in which this interference actually makes your localization, gives you localization in plaquettes. You can study Anderson localization that was beautifully implemented in the group of Multiseger, or you can use topology to create corner modes, for instance, and then make a laser at a corner mode, a localized mode. Okay. So in all these systems, what you are playing with really is with interference. Okay. So it's simple interference. So you just engineer your local potential, this part here, to have interfering modes. So your modes, you can think of them as emerging from an interference phenomenon. Okay. So this is very clear here, where you have the interference that arises from the photonic crystal and the photonic gaps that you create. It's also very here in this plaquette states in which you have a plus wave function here, minus here, so it interferes destructively here, and this creates an isolated plaquette in this flat band. Okay. So to do that, basically you need to engineer your local potential in the right way. So what I want to show you is that in lattices with in which we have losses and that you can also drive, okay, you have extra ingredients to play with interference effects. So this is the typically, I show you, this is the typical Schrödinger-like equation that you have in lattices of resonators or coupled waveguides. But in this kind of lattices, in the ones in which that we usually use with polaritons, you also have the losses, okay, and you can have a coherent drive. So you can put a laser in the drive, and this gives rise to new opportunities to engineer interference effects. So this is what we are going to see. So I'm going to introduce you this lattice of semiconductors in which we use very quickly because you are familiar with them. Then I'm going to show you how we can engineer these localized modes, and in the end, I will discuss some nonlinear effects. How we can how these nonlinearities add again an extra ingredient to this physics. So the lattices we use are based on these micropillars. So you have this black mirror on the top, black mirror on the bottom. You trap light in the middle, and then light is also trapped from the sides because of the index of refraction contrast. And then you have like a photonic atom here with modes that are well isolated. So you have the ground state mode here. It has this S shape. You have these P modes, isolated modes. This is an experimental image in which you can see them in space, okay, for a micropillar. So this is the building block we use to engineer our tie binding models with lattices. So if you put two of them together, now that you make them overlap, and then photons can jump from one micropillar to the other, okay? So that's how you control the hopping. And by playing with the distance, you can control really this hopping in a nice way. And then you can do one-dimensional lattice, for instance. Okay, sorry about the image, but you can make these one-dimensional lattices in which now you can like jump across the lattice, and then you have in real space you have a band here. You can see it, a gap, another band. The second band comes from the coupling of these P modes, this one from the S mode, and if you look in momentum space, you have what you would expect. So you have a cosine-like bands for the S modes and more complicated bands for the P modes. Okay, so this is our building block. So this you can understand it from tie binding arguments. Okay, so no drive and dissipation yet, but let's see what happens when you have drive and dissipation. So let's consider this one-dimensional lattice. Okay, this one-dimensional lattice of these micropillars. So again, I'm writing down the equation that describes this, the dynamics in the system. So you have the derivative in time, the eigenenergy of each micropillar, and I'm considering now the S modes, the hopping, okay, from one pillar to the next, okay, the losses and the drive. So let's see what happens. What are the not the eigenstates, but well, if you look at the eigenstate of this part here, okay, of this part, you have the dispersion I just showed. And let's see what happens at the steady states. So what are the possible steady states when you put a drive, okay, with a given frequency? So I'm choosing a drive that has this frequency, okay, is 0, which is the frequency of the eigenmodes of an individual pillar, okay. We are pumping in this side, and we are seeing, this is a numerical simulation, we are seeing at long time, what is the distribution of light, okay? So you see you have a lot of light in the pump, inside you are pumping, and then you have an exponential decay to each side, which comes from the lifetime, okay? particles move away from this side, and as they move away, they are lost by the losses. So this is what you would expect. Now let's see a more complicated situation. Now let's put 2 pumps. I'm putting 2 pumps now, one here and one here. Let's look at the steady state situation at long times. What happens? So this is a simulation of this equation. In this situation, you see that I am zooming now. So this is my site number 100. This is my site number 105. Okay. You see, I have a lot of light in this side, which I'm not pumping, and I have 0 light here, 0 light there, these 2 sides, and no light anywhere else. Okay. So I'm localizing light at the pump at the site. I'm not pumping between the 2 pumps. So this is very surprising. Okay. And intuitively, you can see that this has to come from some interference effect. And indeed, it's the case. If you look at the time evolution of the solution of this equation, you can see that you start at time equals 0. I switch on my pumps. Okay, here you see I have light in the 2 pillars I'm pumping, and then very quickly you have some interference effects. Very quickly, I get a very strong emission from this side. Okay, and a very long time there is nothing anywhere else but on this side. Okay, there's really an interference effect that constructs after some time in the system. And you can also check that it's an interference effect if you move the frequency of your pump. Okay, I'm putting it away from this E0, and I'm destroying the effect. The interference is not perfect anymore. I still have some localization at this side, but now I have also light away from that side in the lattice.
Is the reflection from the ends of the chain important in this interference? No, so it can be absorbed in infinite.
Right. Yes.
So what are the boundary conditions? It's an open chain.
So in my simulation, I don't do an open chain, but I make it long enough so that there is no light. I mean, when light goes away, if I pump with one side, okay, I am too far away. I mean, the edge is too far away, so that when I'm at the edge, there is no light because everything went away. Okay, so you can think of it as an infinite chain. It's effectively infinite. Okay, so how can you understand this? Okay. So you can try to model it a bit mathematically. So the simplest way, the way I can do it myself, so I'm not a theoretician, so the way I can do it myself is the following. I assume that the losses are very small compared to the hopping, so then this term goes to 0. Okay, that still needs to be there. I need to have losses, but I assume it's very small. Okay, so then this equation in the steady state, so this thing goes to 0, looks like that. Okay, very simple. I have some detuning that I define there, and you work a bit with the equation. You can find actually solutions. You can see that there are values of delta of this detuning. There are values of delta for which the pump sides, the sides you pump, are 0. Okay, so you have steady states for which the pump sides are 0. Okay, and you can demonstrate that if your pump sides are 0, anywhere else away from the pump sides, except for this guy, needs to be 0 also. Okay. So you see that there are situations in which this happens. And what is the condition for this to happen? So which values of delta gives you this kind of solution? The ones I just showed you. So the values of delta that gives you this kind of solution are the values of delta of this detuning, actually, that correspond to the eigenmodes, the energy that corresponds to the eigenmodes of this isolated pillar. So of the pillars that are between the pumps. Here I only have one. Okay, I only have one. So the eigenmode of one isolated pillar is E0. Okay, is this energy. So this thing happens for delta equal to 0 in this simple case. But if now I put the pump, for instance, 2 sides away, then I will have two energies at which this thing will happen, which correspond to the bonding mode of these 2 pillars in the middle and the anti-bonding. Okay, I don't know how you follow. Okay, so this intuitive picture or phenomenological rule to get this interference effect can be applied also to 2 dimensions. So this is an example. This is a square lattice, okay? And I am pumping these 4 guys here at the same energy. So the laser at the same frequency, okay? So I'm surrounding one side. So then if I apply my rule, the phenomenological rule that I found, I should have an interference effect that gives me light here and nothing anywhere else, exactly, again, at E0, at the energy of the unisolated like micropillar. And this is exactly what happens. This is a simulation, okay? At that frequency, so the frequency of the laser is E0, and I have light here, nothing anywhere else. And I can scan my... Yes?
I mean, there's probably still something outside, right? Because you still have some leakage.
Right, absolutely. So you would have, if this would be this tends to 0, then the light around tends to 0. Okay, but if you have some decay, the interference effect is not perfect. You will have something. I agree. You have something, but it's look in this simulation with this color scale. Okay, it's a color scale. You kind of
the gamma goes to 0, or the amplitude outside goes to 0.
Exactly.
And this gamma is equal to 0.
I mean,
just put it to
you need losses. You need losses.
No, let's say you just remove it. What happens?
Okay. If I remove this term,
Yes.
I have a source term,
Yes.
and I will not have any decay
What
term.
will happen? Will you get waves which run to infinity?
I must admit, I have not done the simulation. I have not done the simulation.
But thank you. Then E0 you assume to be constant, right? But if you pump, as you know, I mean, you have blue shifts related. So when does the physics break down? Did you try that in experiments?
I will show you at the end. I will show you at the end. Okay. I will show you at the end. Just let me show you that here. If I move the frequency, so if I change the frequency of my laser by keeping these 4 spots all with the same amplitude, okay, I can calculate the inverse participation ratio, which is a measurement of the localization. So very high inverse participation ratio means I have a very localized state. So this is the case here. For at E0, I have IPR inverse participation very high. But as soon as I move away, you see the inverse participation ratio drops. Okay, which means that the eigenmodes, the steady state modes, are spread away. Okay, so it's again showing you that it's an interference effect, and you need these conditions to happen. For instance, if I now remove one of these guys, okay, I'm not in that situation that I was describing before, these phenomenological situations. I'm not trapping anymore a site with my pumps, and then I see light going away. Okay, and if I calculate the IPR is close to 0 for any frequency of the laser, which means that my eigenmodes, my steady state modes, they are all over the lattice or going away from that. Okay, let's do it experimentally, which is what we like to do in our group. So now I'm not going to use a square lattice, I'm going to use a honeycomb lattice, but the idea is exactly the same. So we have this honeycomb lattice of micropillars. This is the dispersion, okay? You have the Dirac cones on the lowest band, and I'm going to focus on that band, okay? And so now let's try to apply the same kind of like ideas. So if I put one spot, I excite one side, okay? So I'm not trapping anything, so light will just go away, okay? And this is what happens. You see light going away from the side I'm pumping. And if I calculate the IPR, so I move the frequency all over these bands, okay? Move the frequency. You see that the IPR is very low because this is not localized; it's extended. Now let's trap one side. So this is what happens. I put three spots around that side, okay? And at exactly this energy is 0, which is the energy of the isolated eigenmode of this micropillar. I have a strong localization, and I can measure the IPR. You see, these dots is the measure IPR. I have only a strong peak at the energy of E0 here, okay? Which is what I would expect. Nice. So this is a simple situation with just trapping one side, but I was telling you that you can trap more sides. No, for instance, in this situation, I am putting my pumps in this at these 4 micropillars and trapping 2 sides, and then if we apply this phenomenological rule, I will have an interference effect with localization at the eigenmodes of these 2 trapped micropillars, as if they were isolated. So the eigenmodes of the 2 trapped sides are the bonding and the anti-bonding mode. So if I put my pumps in phase, okay, I will have a resonance at the bonding mode. This is the calculated IPR, simulated IPR. You see I have a peak at E0 minus T. This is the hopping, which corresponds to the bonding mode. This is the simulated image at that energy, exactly, that pump. If I now put my pumps out of phase, I will have a resonance at the anti-bonding mode, okay, so at E0 plus T, and this is what we see in this image. So experimentally, I'm going to show you just the bonding mode, but we do exactly that. So we prepare 4 spots like that in phase, and I see a peak of IPR at E0 minus T, and this is the image, the experimental image showing the localization at these 2 spots. Okay. Nice. Okay, so I showed you that we can play with these interference effects, okay, with several pumps, several spots, okay, in the equation, in a lattice. But actually, these interference effects, we realized later, are more general than that. And even with a single bump, with a single spot, you can have interference effects playing with the dispersion of your lattice. Let me show you that. This is a very simple example. This is a photonic molecule. Okay, you have two micropillars, so you have hopping here. So the two eigenmodes of this molecule are the bonding and debonding, as I showed just 1 second ago. Okay, bonding and debonding, same equation. And what you can see here is the transmission of light when I bump one of the pillars, on this one. Okay, and I look at the same pillar and the opposite, the other pillar. Okay, and I scan the frequency. This is experimental. So I see that I have a transmission peak at the bonding mode and a transmission peak at the anti-bonding mode. Let's see how the modes look at this transition. They look like that. So I would expect. This is a simulation, but experimental is the same. You have the bonding mode here, okay, with light in both pillars. You have the anti-bonding mode here with at zero for the wave function in between the pillars. And look what happens exactly here. Exactly here happens something very special. You have no light at the micropillar you are pumping, okay, and all the light comes from the other micropillar. Okay, so why is that? Well, it is because you are actually, I have an explanation here. So this is because when you drag your system at this micropillar, okay, at exactly this point, exactly in between the two resonances, okay, you have a phase shift that is induced by the resonances, okay. So this is the calculation of the phase shift when you go across a resonance or your pump or your drive here. When you go a resonance, okay. If I'm on this side of the resonance, I don't have any phase shift. But if I'm on this side of the resonance, I have a phase shift of pi. Okay. So when I'm here, I'm on the right side of the resonance, okay. So I get a phase shift of pi, but I am on the left side of the resonance, so I don't get any phase shift. So what is going through here is the light that is filling the resonance with a phase shift of pi, and the light that is going through the resonance with no phase shift. So this has a destructive interference effect, and there is no light coming from the pillar line. The light comes from the other. So this is a very general thing, actually, and it happens in any lattice. It happens in any system in which you have parasymmetry, which you have like bands, symmetric and antisymmetric bands or modes that are symmetric, okay, with respect to your pump energy. And this happens here also. Look, actually, I showed you already this image, and you saw that at the energy, at the pillar I'm pumping, there is no light at all. There is only light from all the others. And this is exactly the same phenomenon, okay? Except that now it's happening in the lattice because you're having an interference with all this band here and with all this band here with a pi phase shift, okay, at that micropillar. And then this means that actually you are kind of creating a steady-state solution, okay, in which you have a vacancy state here. So you are exciting a wave function, some kind of like steady-state wave function, in which you have a vacancy state here. So it is a zero of the wave function, okay? And this corresponds exactly, in the case of the honeycomb lattice, to a vacancy mode, okay? And this vacancy mode has been studied in solid-state physics in graphene. And actually, so this is a paper in which they study that in graphene. So they put a vacancy here, okay? And then they look at the zero energy modes associated to this vacancy. And they see that they have a pattern that looks exactly the same as the one we are seeing. You see, they only have amplitude of the wave function, one side out of two, and one of the sublattices only. Okay? But here there is no amplitude, This is exactly the same thing we see in our experiment. So you are creating a vacancy by playing with this interference effect. It is not a real vacancy, it's just I'm playing with interference and I'm creating a zero of the wave function exactly there. So can we use this to do something like a bit of fun in this polarized lattices? So the answer is yes, of course. So let's try with a very simple case. So a very simple case is this S-stage lattice that maybe you are familiar with because it's in many presentations on topology. Okay, so this S-stage lattice is a lattice of coupled sides. Okay, in which you have strong coupling and weak coupling. Strong coupling and weak coupling. So here you have weak coupling and strong coupling. Weak coupling and strong coupling. Okay? So you have two situations. You have the situation in which you end your lattice with the strong hopping here. Okay, this is topologically trivial. You have two bands, a gap, but no edge states. And then you have this other situation in which you end your lattice with a weak hopping, and then you have two bands, a gap, and an edge state. Okay, and it's still localized at this edge lattice. So now you can start to think, what happens if I put a vacancy here in the middle of the lattice? If I put a vacancy there, I will create an edge. So Let's do that. Okay. This is my SSH lattice with polaritons. These are the S bands. Okay. So you have two bands. Okay. The gap. Okay. And I am putting my laser exactly in the middle. Okay. In the same way I was doing with the honeycomb lattice and in the same way I was doing with the time. So if I put in this chiral lattice, has chiral symmetry, my laser here, okay, I will have this interference effect. And if I pump one side, I will excite a steady state mode that has a zero there, okay? Important, it has a zero there. So if I have a zero here, I am breaking my lattice, okay? I'm breaking my lattice here, okay? And I am, on one side, I'm ending on the weak hopping, and the other side, I'm ending on the strong hopping. Okay, so I should have a mode that localizes here on this side, but I am ending with a weak hopping. Look, that's what the separation does me. So I'm putting my laser here at this energy, okay? And I see that my steady state has the shape of an edge state of the SSH lattice, okay? Because this is at zero now, okay? And the experiment looks exactly the same, of course. So I'm putting my laser at this side, and I see that my light comes from that side, locally with an exponential decay, which corresponds exactly to the wave function of an edge. Nice. So going to Sven's question, what happens if you now put nonlinearities? So if you put now nonlinearities, now the situation, I mean, this interference effect becomes more complicated because you have an extra ingredient in interference. So before we were playing with basically interference between this, the hopping, the bands, and the eigenmodes, okay? The laser and the decay, okay? So we were playing with interference between these three terms. And now I have an extra term here that is changing the interference. So for instance, let's see what happens in the, so I don't have any a priori intuition of what will happen. So let's see what the experiment tells us. So let's consider again this SSH lattice. I'm going to pump it again here, okay, at this side. So this is how it looks. So this is a simulation, okay. This is low power, so it's in the regime I just showed you, low power. So I'm pumping here. So in this case, I'm pumping on the other sublattice, but it doesn't matter. And you see I have the localized edge mode decaying on this side. I increase the power, and I start to see like funny effects like a nonlinear threshold here. Okay, and when I go through this nonlinear threshold, I have to increase the power. This localization breaks. Okay, it's not localized anymore on this side. Now it stands on both sides. Okay, I have a second threshold. Okay, and this in the second threshold it becomes more complicated. I have light actually more localized on the other side than I had it here. Okay. So clearly, this nonlinearity breaks the interference I was playing with to have this localized mode, this defect mode, this vacancy mode. But we can actually recover it, okay, in a phenomenological way if we play with more pumps. Okay, so now we're considering two pumps, okay, two spots. We're pumping these two sides, A and B. Okay, and we're going to play with the relative phase between the two pumps. So they have the same amplitude, F. Same frequency, okay, which is zero energy, okay, in the middle of the gap. And we are going to play with the relative phase. And if I go at high power, where I have this delocalization or this symmetrization of the response, you can see here, zero phase difference. This is the simulation I showed you just in the previous slide, okay. Now I change the phase, this relative phase, and I see that at some point, I get localization on one side only, okay, actually on that side, in this case here. Okay, so in this situation, zero phase difference, I have some solitonic solution that looks the same on both sides. And at that phase difference, I change the interference effect in such a way that my nonlinearity is the interference coming from the blue shifts of the nonlinearity actually compensates this blue shift in a way that I get again a vacancy state. Okay. As you see, I have zero of amplitude here. This is block scale, and I have my mode, my edge mode localized on one side. Okay. So this is all very phenomenological. I don't have a wave-handling argument, okay, to tell you why you need two pumps to have this in the nonlinear regime. Okay, it's just that you have more complicated effects because you have an extra term in the interference effect, and then you need to adjust your system in some way to find the useful interference that's what you want to do. So this is basically it. So the main message is here is that now playing with this drive and dissipation in these lattices, you can engineer localized modes, you can engineer like cavity modes, or I don't know how you want to call them, and you have a different response than the one you naively expect from just looking at the type Hamiltonian. Okay, so the mode is playing different because you have this interference, this new interference induced by the pump, okay, by the pumps. I showed you that in the nonlinear regime things are more complicated, okay, and then you have to play with more drives to get similar effects. And actually, all this is very interesting because while writing the paper and discussing with Alejandro González Tudela from Madrid, we discovered that he has been working on lattices, photonic lattices, with quantum emitters. Okay, so you put a quantum emitter in a photonic lattice, or more precisely, you put several quantum emitters in a photonic lattice, and you observe exactly the same effects, exactly the same. So you have localization, for instance. He showed that here he has 4 quantum emitters at these points here, okay, and he has the eigenstate mode, okay, is localized in this area here. So actually, by reading this paper, and there is a mapping between having a drive, an external drive, and having a quantum emitter. Of course, the quantum properties are not there without drives, which is classical, but the localization effects are there. And for instance, reading this paper, we discovered that we don't need this phenomenological idea that you need to go around a site to isolate it from the rest to get a localized mode. Here, they only have 4 quantum emitters, and they are localizing in a site of like 25 sites, okay, in an area of 25 sites, only with 4 quantum emitters, just because of these interference effects. So that's a very nice perspective to go into this kind of lattices with quantum emitters and try to play with this localization. Okay, so I want to thank our collaborators. So this is the group in Lille who did these experiments. Omar Yamadi and Bastian Real, who were the postdoc and PhD students doing this. We have a strong collaboration with Jacqueline Bloch and the group in Palaiseau, who build the samples, and also we have been building understanding of these effects. Samples are built by these people at UN, and we have these collaborations, theoretical collaborations in this works that I commented today. Okay, so with this, I thank you for your attention.
Thank you, Alberto, for keeping on time. So there is a lot of time for questions, please.
Thanks for the interesting talk. So the example you gave of the dimer with the interference, this looks just like a model for final resonance in optics. So I was wondering, so you gave the mechanism here is requiring chiral symmetry. But for final resonance, it's no, you don't need a chiral symmetry at all. It's just a broad resonance interfering with a narrow one. So
yeah, I don't think it's the same thing as a final resonance. I really don't think so. Here, you have the line width here, okay, which is related to this guy. If you make gamma going to 0, okay, this will become a Dirac delta, and you will have the same effect. So it's not really related to a path with a single mode, single site or a single level. It's really related to much simpler physics of these 2 modes, and then when you have a resonance, you just change your phase and you go around. And I don't think you need the Fano. I don't see the Fano aspect here, but maybe we can discuss further.
Okay. If I understood correctly, in the lattice, you said something can switch on and off like single quantum emitters. And is it true? Because the center is not bright. If you have a single photon emitter frame, just by adding the lasers, you could switch it off. Is it true?
No, but let me tell you what happens. So imagine that here, instead of I have my, I will go to this case. Imagine that here I have I have an open microcavity, and I put a quantum emitter at this side, only at this side. Okay, 1 quantum emitter at this side, and somehow I excite it. So I have a 2-level system. I put it on the upper state, and let it evolve. It will the excite emit light into the lattice modes. You have now a path which is made of the lattice modes, and I look at the light that comes out of the system. What I would see is exactly this. I have my quantum emitter here, so I don't have any external laser.
So
I just excite it
to the other mode.
Exactly.
So light will not. Okay.
It will not come from the site in which the quantum emitter is located. It will come from these sites that I'm showing here. But there is no in that example there is no laser. Okay.
Okay.
The role of the laser is.
Now my question is, if you add a laser, you could engineer the light to come out here or there. So this is what I meant with switching.
Okay, sure. So exactly. If I add a laser, what we learn from this, for instance, is that if I want to, if I have a quantum emitter in a lattice, in a photonic lattice, and I want to excite it, how do I do it? Well, I know that if I put my laser on top of the site where the quantum emitter is, I will not excite it. There will be no light there. Okay, if I want to excite my quantum emitter that is located here, now we learned we need to put 3 lasers here, and then I will excite that. Okay, that's what we learned from this work.
Do you want to run this experiment?
Yes.
Sebastian?
Yeah, thank you for this nice talk, Alberto. I was wondering, so here you show, actually from what I can judge from now, a quite decent IPR. I was wondering, when you showed that you can confine these 2 sites in the honeycomb lattice, it was much more modest, exactly. As
correct.
Well, I wouldn't have put it that way, but what I'm really interested in is why is that? So is that next nearest neighbor interaction? Because that would likely also affect the other case, or blue shift. So what do you reckon is
the nearest neighbor interaction plays a role, okay? So for instance, here, you see this IPR should go out to almost 0.5, okay? Yeah. This is the simulation. And because in this model, we have the nearest neighbor interaction, it goes to 0.30 something, okay? But that's not the, I mean, here we have 0.08, okay? It's really bad. So the reason is that we are not as good experimentalists as we would like to be. And when we put our lasers, our 4 lasers around, okay? For this to work like that, they have to be exactly in phase.
Yeah.
And our 4 spots are not exactly in phase. And then when you are not exactly in phase, you break a bit the interference effect. Still, what is surprising to me is that with this 0.08 IPR, you have a lot of light in these guys.
Yeah.
You also have light around because of that effect, because of this, because the phase is not perfect.
Yes.
But it's not perfectly the same in the 4, but
I mean, you convolute with some Gaussian excitation speed anyway, right? So, but do you use a spatial light modulator?
Yes.
And it's still difficult to get the.
I must admit that we are not super experts on SLMs. I'm sure if some of your students who work with SLMs for a long time come to our lab, they will solve this problem.
Let's talk about that. Yeah. Okay. Thank you.
Yeah, question over there.
Thank you for an interesting talk. I have one question and a comment. Probably I'll start with a question. Do I understand correctly that you can do something like inverse engineering? Imagine that you know the sites you want to excite, and then you can calculate the pump distribution needed to obtain this configuration of the state.
Absolutely. And actually, this is one of the lessons to get from here. If I want to, well, I show you, if I want to excite this pillar, I should not just put my laser on the open pillar. I should do something else. Okay, so it's exactly what you said.
Thank you. And then I'll say a comment. This is stuff with excitation of 2 pillars when all energy goes just to one. It reminds me so-called dynamical damping, which you can find, for instance, in washing machine when the suspension system consists actually of 2 coupled resonators, and they tuned like this, that the inner part is vibrating, but the outer part, which is the body of the washing machine, is steady. I think it's very much similar to what you find in optics.
I fully agree. This model is, I fully agree. I mean, this model is just a model of like a couple resonators. Yeah. So you have 2 pendula, okay? You have 2 pendula connected by a line. There is a frequency at which if I drive this guy will actually not move. The one I'm driving, okay?
Yeah.
So it's exactly the same thing.
This is exactly what's used in centrifuges and in washing machines, stuff like that.
Actually, I looked for, when we were writing this work, I looked for models of mechanical resonators that would have observed this in physics already. And I couldn't find any in the range of optics, mechanics, of the mechanics, all that, because people in those micro nano systems, they are very much interested in nonlinearities. So they quickly go into nonlinearity, okay? And they don't really study this. But I should have looked into washing machine interaction. That's what the right thing to do.
Could you please go to previous slide? Oh, and once again. Okay. Okay, anyway, so when you were dealing with graphene and when you were exciting the two neighboring sites, you just have a detuning equivalent to the energy of bonding or anti-bonding levels in this system. But it seems to be different from the case of 1D chain, where you have some different energy from the zero, which is energy of single pillar.
No. It's. I mean, here there is a little bit of complexity because you have this next nearest neighbor hopping. Okay, so the bands here, the bands are not symmetric. Okay, with respect to zero. Okay, so this has a little bit of it makes the things deviate a little bit, but this is the E0 energy. Okay, and this resonance happens at the bonding, so E0 plus T, and the resonance happens at the anti-bonding, so E0 minus T. So it's really exactly the same as in the 1D chain. The 1D chain, if I would isolate 2 micropillars, I will have a localization in these 2 micropillars, okay, at E0 minus T and at E0 plus T. It's exactly the same.
I mean, just the excitation of single pillar in the 1D chain.
Excitation of the single pillar in the 1D chain.
I remember that it required the tuning not equal to 0.
No, yeah, it requires the tuning equal to 0. It happens at the beginning.
Okay.
For one side.
One side.
For one, okay.
2 you will have 1, E0 plus T, E0 minus T.
Okay, more questions? Yes.
Staying here on this slide. So if you go to 2, you will still have the same feature in this 1D example, that you have essentially 0 amplitudes outside, even on the next side, just to the right of one of those guys.
Exactly 0. If gamma is small, it will be very close to 0.
And back to the nonlinearity, you were tuning it and you saw some breaking of, or not, some switch from, so to say, localized on the right to localized on the left.
Yes.
Is that similar to throwing nonlinearity out of the window and just tuning the strengths of the pumping? If I forgot what you showed.
Yes, I'm not sure about that. Yes, I see what you mean. It's like the idea is, can you find a situation in which you can just rewrite this equation just without the nonlinear term, and I understand correctly your question, and to have an effective equation that is not this becomes linear now.
I'm not sure, or maybe you just have to change the frequency. No, it's a tuning of the frequency, maybe, isn't it? Yes. Because you change the.
So let me tell you something. So actually, this the group of Alejandro González in Madrid, they have got interested in this topic. They actually wrote a paper doing the mapping between the quantum emitters in the lattice and our system. So it's the mathematical mapping, they did it. And they have been working on doing this, as I'm showing you here, but changing the energy, okay, at high power and in a linear region. And basically what they see is that when you change the energy here, okay, you lose the localization, but if you put the right power, so you put the right nonlinearity, you recover it. So you have some kind of like bound state in the continuum that you can drag all over the lattice, okay, thanks to the nonlinearity. So you kind of like compensate the misinterference with the nonlinearity. And they are trying to understand why it happens and what the mechanism.
Okay, there was a question at the end. Yes.
Thank you for this nice. So, simple question. Have you investigated this effect due to non-linearity in 2D lattice?
No.
Like a normalization of density?
No, I mean, one thing we are preparing now to do is this thing I just mentioned, that in this honeycomb lattice, you can have this bounce into the continuum, okay? When you put your laser out of here, you can recover this interference effect localization thanks to nonlinearity. Our collaborators are working on this theory of that.
Okay, very urgent questions now. If not, we have the coffee break. Last question, please.
Yeah, I mean, I just question about this SSH lattice. Yeah, I'm just curious. So to change the hoppings, and you can just control how the pillars they touch each other. But is there another way to control the hopping, not by only touching?
So hopping is overlap of wave function, right? Mm-hmm. So you need to control the overlap of the wave function. So any way, any technique to control the overlap of the wave function would work. I mean, just controlling the controlling the overlap of physical overlap of the pillars is one of them, but maybe there are others. Yes.
Okay.
Okay, I'm sure there will be more questions, but we can ask Alberto during the coffee break. So let's thank the speaker and we see you.